how do we solve for these new internal loads when we have a two-dimensional rigid body? So usually the first step is we want to solve for the external reactions. Like we did with truss problems, if we can solve for the external reactions, let's do that first. Now, the new part is we're going to make this section cut or this internal cut through our structure at the point that we're interested in finding the internal loading. So we're going to decide where do we want to make that section cut, and then we're going to keep everything on one side of that cut. And usually we want to keep the side of the cut where we just have less going on. It will be less in the equations to write and probably quicker to solve. So in this picture at the bottom here, I am going to make the section cut, and in this example, I've kept everything to the right of that cut. Now, typically, we are going to be making a cut that is perpendicular to the longitude of the member itself. So this left picture is going to be more common. However, we can, as long as we're making a cut that goes through the point we're interested in, we could make an oblique cut, but it's going to be typically less common. So now, on that new cut surface that we've just produced, we have to model what were the loads that were keeping the material held together. So first up is going to be this force P, which we call the internal normal force. And always we are going to draw that force P coming out perpendicular to the cut surface. So in this particular picture, since my cut was vertical, P is a horizontal force. It's pointing to the left because that is the outward normal direction from that cut surface. In the example on the right, if I make this oblique cut, P is up and to the left because that is the outward normal direction from the surface of the cut. The direction of P is not dictated by whatever coordinate system you're employing. The direction is going to be determined only by the outward normal direction of the cut surface. This force P is always going to be coming out from the centroid of that cut surface. And by convention, if our force P is positive, that is going to mean that we have a tensile internal normal force. And if it's negative, it's going to tell us it's a compressive internal normal force. Then the next load is going to be V, which is called the internal shear force. Now, in this picture, it is parallel to the cut surface, and that's always true. I have assumed its direction here to be up on this cut surface, and then on the right-hand picture where I made an oblique cut, up and to the right. There will be, for beams, a standard convention for what direction you assume is positive, but for right now, we just need to make sure that it is directed along the parallel to the cut surface. Now, when we find the sign on V, it does not have that same interpretation of compression versus tension. That is only going to be the case for the internal normal force, P. And finally, we're going to expose the internal bending moment, M. And that is going to be a moment, and it's going to be acting around the direction that is perpendicular to both P and V. So in this picture, it is acting around the axis that is going into and out of the page. Now again, for beams in strength of materials, there's going to be a standard convention of do we assume clockwise or counterclockwise. For right now, like in this picture, I am just going to be drawing it clockwise here, and I'm going to let the sign tell me if I'm right or wrong. But later on, there is indeed a convention we need to adhere to. Now, in this picture from the section cut, just for illustration, I took everything to the right of the cut. If I had taken everything to the left of the cut, or if I, in addition, draw the section to the left of where my cut is, I am obligated to assume the opposite directions for V and for M, and for P as well. But again, P in that picture would automatically be pointing to the right because that is the outward normal direction. So what have we done? Taking one of these new internal section cut free body diagrams, we've introduced 3 more unknowns. However, we will also be able to get 3 more equations because this is a 2D rigid body free body diagram. So that means we're going to be able to get 2 force equations and a moment equation out of this. So 3 equations we can get out to solve for these 3 new unknowns. And as I said earlier, typically we are going to be making our cut so that it is perpendicular to the longitude of our member, but we could take this oblique cut. But notice the values we get for P and for V will be different depending on the angle of the cut, even though we are assessing the internal loadings at the same point along the member. This is going to become an important point later in strength of materials.